So this video is all about vector addition. If you haven't already, make sure you go back and watch my introductory video on vectors and scalars, in particular the part about resolving vectors, because that's going to be really important for what we're talking about here. So vector addition. When is this actually used? So we're going to talk a bit about the maths of it, but firstly I wanted to give you a bit of context. So typically we use this when we're finding the resultant of multiple vectors. What do we mean by that? So you may have heard people talking about the resultant force. So imagine you're sitting on your chair right now. You've got force acting downwards, force acting upwards. At the moment, there is zero resultant force acting on you because those forces balance. What we're actually doing when we talk about this is we're adding all those vectors in all different directions together and seeing what comes out. If there's no resultant force, they'll cancel. But let's say, for example, you're in your car and you're accelerating down the road. If you were to add all those different forces together, what would the sum of those be? And the sum, mathematically speaking, is what we mean by vector addition. Okay, so I'm going to talk you through the maths of this first. So let's take two vectors firstly. So we've got this vector here, which we'll call A, and we'll take this vector here, which we'll call B. So what I want to find is A plus B. So the easiest way to do this is to take each of these. I'm going to duplicate these and move them over here. And to line them up end to end, like so, top to tail. Now, the resultant of these is going to be from the start of one to the end of the other one. So here, that red line there is going to be A plus B there. So what we found here is the resultant vector of A and B. And if you like, you can think of this almost as the opposite of resolving that we talked about before. We're taking two vectors here and finding out what one vector between them would be. At least that applies in this specific example. Okay, well, let's put some numbers to it now and see what we can do mathematically. So I'll stick with these directions here. I'm going to take a let's say 3 meters here. So I go 3 meters to the right and then I go 4 meters up. So I'm going to trying to draw these to scale as best I can. That 4 meter arrow should be a little bit longer than the 3 meter arrow. It's not quite there, so let's just stretch it out a wee bit. Okay, so what we're trying to find here is, for example, I move 3 meters to the right, 4 meters forwards. What's my resultant position? What's my final displacement? Okay, so same idea. I'm going to take these two vectors, put them top to tail. In fact, I'm going to do this slightly differently, just to show you it doesn't matter which one you do first. So I've gone with the upwards arrow first this time. My resultant will be from there to there, from the start to the finish. So how am I going to find the length of that arrow? Well, here we've got a right angled triangle. How do I find the length of that side? Well, that's going to involve a bit of Pythagoras. So to find the magnitude, we can do a squared plus b squared equals c squared. Square root of all that should give me the length of that side. If you know your Pythag, that should be 5, and we're talking about meters here. So the length of that arrow is 5 meters. Good, so what we found there is the resultant of those two vectors. If I go 3 meters to the right and 4 meters forwards, I'll be 5 meters from where I started. But we're not done there yet. We're talking about vectors. We found the magnitude of that vector. We also need to find the direction. Well, I've got the arrow there, so I know the roundabout direction, but to do it properly, I need to find out what the size of that angle is. So that's going to involve a bit of trigonometry. I've got the opposite here and the adjacent. So to find that angle, well, that's going to involve a bit of tan. So my inverse tan of 3 divided by 4 will equal, let me just plug that in, 37 degrees. Okay. So what we found there is the angle from which I started, from north, essentially. Okay, so that's adding two perpendicular vectors together. Nice and easy. If I've got more than two, I can create what we call a vector polygon. So I'm going to walk you through one particular example with this to begin with. So we were talking about direction before. Let's stick with that idea. So I'm going to start at a certain point, and then I'm going to walk 2 meters forwards. Again, I'll try and keep drawing this to scale. So I go 2 meters forwards. Then I go 1 meter to the right. So that should be half as long there. Just about. And 1 meter south. It's about that long. Okay. So my question is, what is my displacement from my starting position? So I've got 3 vectors here, and if I go back to what I did before, I went from the start to the finish, and I could do that exact same thing here. That's what I've done. I've put all those vectors top to tail. So if I draw a line from the start to the finish, and the arrowhead's going towards the finish, that is going to be my resulting displacement after going through that journey. So how can I find my resulting displacement? It's going to be the exact same logic that we used before, except this time we've got 3 vectors to consider. So let's have a little look. I want to find the length of that side and that side. So let's start with this one here. So I've gone 2 meters upwards. I've gone 1 meter to the right. Well, that 1 meter is not going to affect the arrow we're looking at. And then 1 meter back down. So in total, I've gone 1 meter north. What about in the east and west direction? Well, I've gone 1 meter to the east. And so this red arrow is going to be equivalent to going 1 meter east and 1 meter north. So how can I find the magnitude of that? So again, it's going to be a bit of Pythag. Square root of 1 squared plus 1 squared equals root 2, which equals 1.4 meters. So that's my resulting displacement there. And just like before, I need to find my angle. So let's go for this angle there. So here, that's going to be inverse tan of my opposite, which will be 1 meter, divided by 1, which equals 45 degrees. So I found that angle there. Okay. Alternatively, you might have chosen to find, let's do it in a different colour there, this angle here. Now that's absolutely fine, provided you label on your picture which one you've found. So here, that's also going to be 45 degrees. Really important that you label the direction that we're talking about here. Okay, I'm going to give you another example here. So let's have a little go. So we are going to do we've got a 4 newtons upwards. We'll have 3 newtons. It's got to be a little bit shorter there. 3 newtons down. 2 newtons to the right. We'll have another 1 newton arrow down. We'll have 1 newton that way. And another 1 newton that way. Okay, so this is a free body diagram showing all the different forces acting on an object. So what I want to do here is to find the resultant of all these different vectors. So let's have a look go at that now. So let's start by taking all these different vectors and putting them together. So it doesn't matter which order I do them in, as I mentioned before. So we've got a 2 Newton arrow acting that way. We've got a 3 Newton arrow acting, oh, we'll go with the 1 Newton arrow acting down. Oops. Let's just draw that one on. 1 Newton arrow acting down. We've got a 1 Newton arrow acting to the left. We've got a 3 Newton arrow acting down. And we've got a 1 Newton arrow acting to the left. Okay, so I've made my vector polygon here, where I've put all those forces top to tail, and what do we notice? Well, I started at this corner here. When I put all those vectors in, what you'll notice is that I finish at exactly the same point. So a closed vector polygon, as in I start exactly where I finished, what does that mean? Well, if you consider this as all the forces acting on an object, if all the forces forwards equal all the forces backwards, all the forces left equal the forces right, what's that going to mean? Well, that's going to mean there's no resultant force or no resultant velocity, whatever you're using here. Really important there, if you've got a closed vector polygon, you've got no resultant vector. Okay, so what happens now if we have non-perpendicular vectors? So to give you an example, we were talking about forces there, so we'll stick with that for this example. So let's say I've got a 5 Newton upwards and 4 Newtons, which is going to be slightly shorter at an angle of 30 degrees to the horizontal. Okay. So, what I want here is to find the resultant of these two vectors. How are we going to do that? So, I've put them top to tail already. So what I want to do is I want to draw an arrow from the beginning to the end, and that's going to be my resultant. So how am I going to tackle this? Before it was nice and easy because I could add all the vertical bits and all the horizontal bits and it all worked out. Here, this guy is causing me problems because it's not completely vertical, it's not completely horizontal. So, if you watched my previous video, hopefully you're familiar with how we can resolve a vector. So, let's have a little go at that now. This 4 Newton vector, I can split this up into its horizontal component and its vertical component. So, what's this going to give us? So, if you remember my rule, let's start at the hypotenuse. If I go to the horizontal component first, I've gone across the angle there. So that means this horizontal component will be 4 cos 30. The other one, therefore, will be 4 sine 30. So, and if I put that into my calculator, that will give me 2 newtons, and this will give me 3.5 newtons. Okay, so how does that help me? Now that I've split that 4 Newton arrow into its horizontal and vertical components, why is that useful? Well, let's see how that can help us. So what I've got is I've got my original 5 Newton vector going upwards. As I said, it doesn't matter what order I draw these in, so I'm going to just draw that 2 Newton arrow first, and then we got 3.5 newtons in that direction. So now hopefully things are becoming a bit clearer. Now it's really obvious exactly what my right angled triangle is. I've got 7 newtons up and 3.5 to the right. It's a bit of Pythag here. 7 squared plus 3.5 squared, all square rooted, should give me the magnitude of that line, which will give you 7.8 newtons. And the direction, as we mentioned before, so I can either find this one or this one. Either one's fine. So let's go for that one. In this case, it's going to be my opposite over my hypotenuse. Sorry, opposite over my adjacent. 3.5 over 7. which will equal 27 degrees. Alternatively, what you could have done is found that length there, which will be 63 degrees. So that is how we resolve non-perpendicular vectors. What you have to do for every vector that doesn't fit into your up, down, left, right coordinate system, you will need to split that up into its vertical and its horizontal components. What do I mean by that? Well, I'm just going to give you a quick example here. If I've got a free body diagram with all different forces acting on an object, 4 newtons, 3 newtons at a certain angle. I've got a 2.5 Newton arrow at an angle of 42 degrees. Okay, so looking at these forces, I've got these 4 different forces acting on the object. I would need to split this vector and this vector into its horizontal and vertical components in order that I can draw a vector polygon to work out what my resultant will be. So that's how I would tackle it if I had lots of different vectors all in different orientations. Okay, so to finish this video, I'm going to give you a question to have a little look at for yourself. Dr. Roach is going on a walk from his house, walks 5 kilometres north, before turning and walking 7 kilometres northeast, before turning again and walking 2 kilometres south. So first part is to construct a vector polygon. Pause it now, have a little go at this question, and then we're going to go through it. Okay, so my vector polygon here. Try and draw this to scale as best I can. I've got a 5 kilometre vector to the north. Then I go 7, so it should be a bit longer there, 7 kilometres northeast. And then I go 2 kilometres south. So, how am I going to tackle this one? So just like before, this arrow here does not fit into my north, south, east, west coordinate system. So I'm going to have to break this one up into its vertical component, which will be that one, and its horizontal component, which will be that one. Okay, so I've not been given an angle on this question though, so that makes things a bit trickier. Well, if you know your compass bearings, you'll know that, that northeast is on a bearing of 45 degrees to north. So that helps me out. So here, what are we going to have? So this component here will be across the angle, so that's going to be 7 cos 45, which happens to equal 4.9 kilometres. This one here will be 7 sine 45, which also equals 4.9 kilometres. So now I've got this in a form that I can solve it. So my final displacement from my starting point is going to be from the start to the end. So that's my displacement. What I want to find is the magnitude of that pink line and the angle. So I'm going to just redraw this ever so slightly over here so we can make things a bit clearer. In fact, I can just duplicate that whole lot. So let's get rid of that one because it's not helping anything. So how are we going to tackle this? So I need to find the length of this vertical pink line, which will be 5 plus 4.9 minus 2, because that's in the opposite direction. So that should give me 7.9 kilometres. This horizontal line here is going to be 4.9 kilometres. So with a bit of trick, we should be able to find that the magnitude of that line will be 9.3 kilometres. What about the bearing that I'm on? Well, that's going to involve some trigonometry this time. So that should give me a bearing of 32 degrees to north. Or, as I mentioned before, that will give you 58 degrees relative to east there.